Good morning. Today's lesson is the second in the series on rocket stability. This particular lesson, we're going to be focusing on the center of pressure. So if you notice in this image from a NASA resource, the center of gravity is indicated by the upper solid yellow circle, and the center of pressure is indicated with this yellow circle with the black dot in the middle of it. When we design a rocket, you want to design it so that the center of pressure is below the center of the gravity. And the reason why we do that is because the way that the forces act, if your rocket tips, the forces act opposite to correct that that rotation. So as you notice here, where the rocket is facing to the right, the lift is causing a little bit of a pressure here on the bottom of the rocket to the right, which then will stabilize it back into a vertical orientation. And then over here on the right side, where the rocket is tipped more to the left, notice that the lift vector, or the direction of lift, is actually pushing to the left on the bottom of the rocket. And so what happens is that then reorients the top more to the right, and again straightens that rocket out. So by keeping the center of pressure below the center of gravity, so the center of gravity is going to be like the fulcrum of a lever, it ensures that whatever direction the rocket tips, that the center of pressure pushes in the opposite direction, so that the rocket will right itself back into a vertical alignment. So to do this, we're going to use the fins. The fins are the primary driver of the location of the center of pressure. So to design our fins so that our center of pressure is in the right spot, we're going to use something called OpenRocket. Now, unfortunately, there is not a Chromebook version of OpenRocket. So in order to use OpenRocket, you have to have access to a laptop or a desktop computer. So if you're having trouble with that, please let me know, and I will try to figure out a way to accommodate that. Maybe we can check out one of the laptops that we have at school, or maybe you could come in, or maybe somebody could enter the information for you. We'll figure something out. So if you don't have access to a laptop computer that you can open OpenRocket on, please let me know. But basically, the URL is here at the top of the screen. You can Google OpenRocket. It's like the first thing that pops up, or the link is also in Google Classroom. Once you get to the right web page, click on this big blue button that says download version 15.03, and it will execute what's called a jar file, which is essentially a Java applet file that should open automatically into this screen. Now, I've already done some of the work. I've laid out my entire rocket. So I used one nose cone and I used 2 body tubes. Notice over here, my nose cone is pretty much by itself. I made the length 10 centimeters, measured that right off my rocket, and I made the diameter 11 centimeters, again, measured that right off my rocket. If you don't have a tool that will measure in centimeters, there are a number of calculators on the internet that will convert inches to centimeters. So if you're having trouble with that, just Google, inches to centimeters, and you'll find a calculator that you can use to change that. My thickness, I set at 0.1 because I used a plastic bottle. So, and they didn't have plastic on here, so I just set it as paper. It's probably a little lighter than what it really is in real life, but, it's not going to be off by that much. And then the shape parameter really decides how triangular versus rounded your nose cone is. I used a bottle, so it's not quite perfectly triangular. So I kind of went with a little bit in the middle where it's a little rounded, but it's pretty triangular. For my top body tube, I've included a mass. So to include an unspecified mass, you click on the body tube and you click on, oops, I got to scroll down here, mass component. So remember, this is where my crew capsule is and where the center of mass for my egg is. So when I open up that mass, it's about 100 grams. That's what I used in my calculations. I didn't pick a density. I didn't think it was relevant. I put about 2.5 by 2.5 inch diameter for the egg, and I made it an offset of 11 centimeters, so from the top, so that it was about where my X was that I had drawn on my body too. I also added a parachute. I was just playing around. You don't necessarily have to add that. It does add some mass to it for the calculation of the center of gravity. So, and again, you can set a lot of the parameters. You can say the diameter, drag coefficient. We have no idea what it is without actually measuring that. I just left it at what was already there. I added the shroud lines, the line length, and then I put it that it deploys 5 seconds after the ejection charge, and I offset it from the bottom component up into the top one. So that's how I placed it in that spot. And then I also added inner tubes. That's where our engine mount is down here. So that's these here. I added 4, and then I put them in a cluster motor design with a slight separation of about 1.5. And then the motor overhang I have ejected about 1 centimeter below the rocket. It's hard to see on the drawing, but I did show that as it kind of sticks out a little bit out the back. And then I added another unspecified mass down here to the motors to represent the weight of the motors. So I used 200 grams, and I just left 2.5 and 3.5 as the size of it, because it's really more about centering it at the center of gravity. So that's basically the majority of my layout, and notice that the calculations that I did are pretty accurate. The center of gravity is right about where we have the 2 stages separating from each other. Now, this red mark here, that's the center of pressure. So I added these trapezoidal fins. So I clicked on here. There's a number of different fins shapes that you can use. It doesn't matter which ones you use. I chose trapezoidal because that's my preference. Now, a couple of things about fin design. You want them to hang out the back of your airplane or your rocket. This will support the rocket on the launch platform, and you need enough room underneath the rocket to be able to put in the igniters and the wiring to launch the cluster motors, and you don't want them to be touching the metal, because if they touch the metal, then it shorts and you don't actually launch. So we need enough space underneath the body tube where your engines are to be able to put the wiring harness and the igniters in and have them not actually touch the launch pad. So that's why I have mine sticking out the back end. Also, just from past experiences, it's more stable if they're flat on that surface than if you have them, at an angle where the entire fin isn't sitting stably on the surface. So if you click on the fin, notice that there's a lot of different things that you can change. I decided I wanted 4 fins. You can put whatever number of fins you want. The more fins, the more mass you're adding to your rocket, obviously. The less fins, the less mass. But the number of fins is also going to affect the directions that the air puts pressure on your rocket and will affect where the center of pressure is. The root chord is going to be the length of this inside part of the fin. So notice when I increase it or decrease, whoops, I've already got it too, but why is it not changing? Why is this being finicky? I have to, looks like it locked up on me. Let's try this one more time. Alright, so there we go. Notice when I change it, that inside length is changing back and forth. And notice as that changes, it's moving the center of pressure. Now remember, I want to keep that center of pressure below my center of gravity, and I want it about a body tube below. So I'm eyeballing it. Obviously, this would be not far enough, and this would be probably too far. Those fins don't look stable either. So I'm kind of trying to put it eyeball from the center of the blue dot to the center of the red dot, about a body tube below. And so that's basically what I'm doing here. I'm just kind of manipulating these different pieces until I have the center of gravity where I want it, and the shape of the fins kind of what I want. This position relative to the bottom of the parent component, this is what moves the fins up and down below the rocket. And notice as I move them up and down, that center of pressure is moving up and down as well. The sweep length is going to change kind of the angle and the direction that the trapezoidal sweep happens. I want, again, to maintain about a 90-degree angle with the surface of the launch platform. So I want to keep these kind of flat on the bottom, my sweep length. The tip chord is going to adjust that outside edge of the fin. So going from like a triangle more into a trapezoid. And again, I can use that to adjust so that the bottom part of the trapezoid is pretty much a 180 with the launch surface. So I messed it up a little bit here. And so you just play with those measurements until you have a fin shape that you like, as well as the center of center of pressure where you want it. And then once you have what you want pictured here in the drawing, then you want to use, I shouldn't have closed that, you want to use these measurements then to draw and cut out whatever number of fins that you're using. So again, remember the root chord is the length here on the end, the next to the body tube. The tip chord is the length out here on the far outside edge of the fin. Your height is how far it comes out from the rocket edge here. And with those 3, you should be able to pretty well approximate the length of your and the shape of your fins. And then when you go to glue them on, this number here is going to be important because this 7.6 centimeters is how far mine dangle out away from my body tube. So there you go. You're going to be using those measurements then to cut out however many fins. In my case, I'm going to be doing 4 fins out of cardboard. And then gluing those to your rocket. And it's really important at this step that when you're gluing, that you glue them nice and straight and that you glue them at really geometrically balanced angles. So in my case, I'm going to be drawing them or gluing them at 90-degree angles from each other because this is entirely what's going to affect the stability of your rocket and decide whether it goes up or whether it flies sideways and ends up crashing into the ground. So there you have it. This is rocket stability part 2.